Christian Timmerer is a full professor of computer science at Alpen Adria Università, Klagenfurt Institute of Information Technology, and he is also the director of the Christian Doppler Laboratory, Athena. His research interests include multimedia systems, immersive multimedia communication, streaming adaptation, and quality of experience, where he co-authored more than 20 patent applications and more than 300 articles. He was the general chair of many conferences, WIMIS in 2008, COMEX in 2013, MMSP in 2016, and PV in 2018, and has participated in several European-funded projects. He also participated in ISO MPEG work for several years, notably in the area of MPEG 21, MPEG M, MPEG V, and MPEG-, where he also served as a standard editor. In 2012, he co-founded Bitmovin to provide professional services around MPEG-, where he holds the position of the Chief Innovation Officer, Head of Research and Standardization. So Professor Christian will give a talk today on HTTP adaptive streaming, Quo Vadis. Christian, you have the floor for the talk.
Thank you, Wasim, for the kind introduction, and thank you for inviting me here for this talk, HTTP adaptive streaming, Quo Vadis. Quo Vadis is a Latin term and means something like where are you heading or where are you going to? So let's see where this will lead us. But before we start, I usually try to have a kind of motivation slide. I guess everyone knows the Moore's law, like the number of transistors in an integrated circuit doubles about every 2 years, and the graph on the right side is something that you probably are familiar with. There is another law, Nielsen's law of internet bandwidth, that says the user's bandwidth grows by 50% per year. And if you go on this website, there is also, you find updated information. The latest update, it seems, is like from 2023. And it seems to be true, although in general, it's about 10% less than the Moore's law for computer speed. And also in terms of video on the internet, it accounts for more than 65% of the global internet traffic. And there is this Sandvine Global Internet Phenomena report that I always use in this context, and I will come back to this later again. Wasim already introduced me. I also have this slide here, and I will just skip it. Yes, I'm a professor for multimedia systems and present in this capacity here. Where can you find me? So that's our campus, and actually I'm in this office right now, giving you this presentation. There is the lab, the Christian Doppler lab at Athena is in this office here. And yes, now summertime here, so we have nice weather, so we also go swimming to the lake, and so do our students. What is the agenda for today? I give you maybe an introduction to why this research is happening. I give you a brief overview about what we did in Athena in the different areas. You see a lot of bullet points here. I will come back to this later, and in the end I want to give a conclusion and also a bit an outlook where we might end up in the future. Again, why doing this? I said this already. I usually take the Sandvine Global Internet Phenomena report here. The newest update is from January this year that basically states about 68% for fixed or wired networks and 64% for mobile internet is video. So video streaming is dominating today's internet traffic. You also can see that for different video on demand and live, it is a bit different. Again, for fixed and mobile networks, main applications here are YouTube and Netflix. They are each of them more than 10%. But you see between the streaming part and the rest, there is a big gap. So the majority of the internet traffic today is actually related to video, and also video in these applications continue to be of enormous demand in today's homes, and also requires lots of internet and significant bandwidth demands. If you look, for example, at UHD virtual reality, we go into the domain of like here 500 megabits per second, although this is a report already some years ago, but probably still shows a bit the demands that we will require in the future. And that's why also research, I think, in this area is a good thing. How does HTTP adaptive streaming works? And I still use this slide that the student made, I think like more than 10 years ago already, but it still shows very well on how it actually works. So you just need an HTTP server where you host the video content, and each video content is provided in different quality. Here in an abstract way, only with low, medium, and best. And over time, each of these versions, you basically chunk into smaller parts, which are sometimes called segments. And then each of these segments are addressable over HTTP by the client. The client receives a manifest, knows what is hosted on the server, and then based on the bandwidth, it can make HTTP requests to these individual segments depending on the bandwidth. So when the bandwidth is low, it can segment low quality. When the bandwidth goes up, it can increase the quality. If the bandwidth goes down again, it again can decrease the quality, which will result in a smooth and hopefully good quality of experience at the client and the user side. How this adaptation is happening on the client is not defined in any standards. It's subject to research and development, and I will come back later to this in more detail. But what are the general multimedia systems challenges and trade-offs that we have to do here? It can be explained by this triangle of content, time, and quality. Content refers to the content complexity that ranges from this traditional audio video, like we have it right now in the video conferencing system, but also going into augmented reality, virtual reality, 360-degree videos, or even multimodality, multisensory type of content. When the content complexity increases and you need to encode it at a certain quality, you probably need a lot of time to do that. So something like end-to-end delay, startup delay, channel switching, synchronization or interaction, everything that has to do with the time has also an impact then again on the quality itself. And in quality, there are different terms. Nowadays, people talk a lot about quality of experience, which is related to the end user, as you probably know. And if you optimize in one of these directions, it might have an impact on one of the other endpoints of that triangle. And that's why I think it's a good way to present the challenges and the trade-offs that we need to do. Coming to the so-called Christian Doppler laboratory, Athena, which is about adaptive streaming over HTTP and emerging networked multimedia services. It is a so-called application-oriented basic research funding scheme by the so-called Christian Doppler Research Association and the company, in my case, that's Bitmovin. It's quite handy to have this connection here, which allows us to do research over a long period of time. So that's a 7-year project in terms of content provisioning, content delivery, content consumption, and also looking into end-to-end aspects. And now I'm trying to give you a brief overview of each of these, we call it internally work packages, starting with the content provisioning, where the main work item here is video coding for HTTP adaptive streaming. And in that respect, we worked on either quality improvement, runtime improvement, and application scenarios. So in quality improvement, we looked in previously into per title encoding for live use cases, where we introduced the mechanisms for video complexity analysis. I will describe this in more detail, which then allows multiple use cases. Before that, we did some runtime improvements. I have this stuff in an earlier version of this talk. And as already mentioned above, the main application scenario is live for now. So let's start with the video complexity analyzer, or VCA, with the problem statement and the basic idea for live streaming. So far in live streaming, the companies and the services, they use a so-called static bitrate ladder. So they have predefined bitrate resolution bursts for all the content. A couple of years ago, Netflix introduced something which they called per title encoding, where they optimize the bitrate ladder based on the content itself, but they only did this for video on demand. Because it took a lot of time to optimize that. It was not possible for live. But we also see that we have an increase in spatial and temporal resolution. So we have UHD or HFR, high frame rate content, which is also a bit motivated, I think, here with the different resolutions and different bit rates. And if you do the encoding over a bit rate with a certain quality metric, VMAF in this case, the curves, they look quite different, and sometimes they are close to each other. Sometimes you have somewhere an intersection in between. That's why the idea was for live cases to have a so-called perceptual-based bitrate resolution frame rate prediction algorithm based on the actual content complexity. How does it work? For that, we use so-called spatial and temporal content characteristics. It actually goes back to a publication from 2007 that uses an energy function for segmentation and compression, which is based on DCT. So it basically works on all DCT-based encoding schemes and extracts the spatial and the temporal content characteristics, which we called E and H. In the meantime, with version 2, we have 7 features as listed here, and you can find this information also on this blog post, and also VCA is publicly available as open source. So you can try it out and experiment yourself with it. Some of the latest results in terms of performance, we also have measured quite recently, and we compared this with spatial information, temporal information, with the reference implementation, which is of course not optimized. We optimized VCA also in terms of runtime, as you can see here in the speed, in terms of the frame per second, with different options here, if threading options and other features to be included. It can get pretty fast, and as a side result, it also reduces the energy consumption. When we compare it with the VCA results with respect to the spatial information and temporal information, it also shows good correlation, as roughly shown here. I don't have the time to discuss all the details, although later on we saw, and that's why also we tried to improve VCA with a new version that is called enhanced VCA or eVCA, that is also improving in terms of the temporal complexity a bit better than the current VCA results. What can you do with that? In live streaming, as briefly shown here, so you have the live media range just here. You can do in real time, do a complexity analysis, extracting the spatial and temporal characteristics using the VCA tool, which can be also used then for scene detection based on these characteristics. And you can adjust the encoding profile for an optimized ABR profile, that's how it is called in industry, with a different bitrate ladder for every scene. And you can use then more or less a title encoding scheme in live. Whereas in the regular encoding, you just have a predefined static bitrate ladder that you use for the entire duration of your live stream. Just imagine you have a 24/7 live stream. The content characteristics might change during that live stream quite significantly. And with the VCA tools, it allows you to optimize and update the encoding parameters during the live streaming for improved quality or for lower bitrate, depending on how you want to configure it. The idea is just shown here, quite simple. Depending on the content characteristics, you have here, like it's called middle, simple, and complex content characteristics. If it is kind of middle, you have like different resolutions up to 4K with high bit rate. But if the content becomes very simple, probably for 4K content, you may even just need 3 megabits per second. And if it becomes more complex, you skip the 4K resolution, but encode 1080p with 10 megabits. So that's how kind of the idea on how you can do it. And you can do it for every shot or every scene or every short period of video segments, depending on how you want to configure that. Here are just some encoding examples with the standard or the live per title. Probably you don't see that much difference here now on the small, but if you zoom in a bit more, you have a bit of a different quality here. On the left is the static, on the right is the per title encoding, and the quality gets a bit better here, as you can see in that screenshot here, and that was also shown at NAB show, I think 2 years ago. Of course, we did lots of evaluations, and one was related to where we called this online per title encoding, OPTE, and then showing across a different set of data sets that overall, when looking at the Biontech delta on the bitrate, taking VMAF or PSNR as a measurement, it could reduce about close to 28 and 20% compared to a static bitrate ladder configuration. It's also shown here in the image here, and there are multiple of other approaches and evaluations that we did in this case, showing good improvements compared to when using a static bitrate ladder. But it's not the end of the story, because we also noticed that sometimes the encoder configuration is a bit weird, that using encoding points for the different quality versions in the streaming scenario, where the difference between two adjacent representations is very low, which means we try to come up with something which is called perceptually aware per title encoding, PPTE, that's how we called it, and got published in ICME 2022, coming up with the idea, okay, how about we distribute our representations across the VMAF score according to the so-called just noticeable difference, making sure that when you jump from one representation, from one bitrate to another one, there is also a quality difference. Just noticeable difference concept is probably well known. And here the idea is, okay, if we switch from a lower bitrate to a higher, or the opposite way, there should be a difference, should be an improvement in the quality. Otherwise, switching up probably is not worth doing so. And with PPTE, we could solve that. We defined an algorithm where we then could, again, depending for VMAF and bitrate with a HLS bitrate ladder, we could still improve the bitrate here, also reduce the storage. And then the last column here is kind of the average JND in terms of VMAF scores, which is roughly or close to 6. And this number 6 is something that for some reason a journalist picked up, put it in an article, and everyone is using it now. And it dates back to an interview of that journalist with the Netflix engineers that gave them this number. And that's it. We have a paper where we investigated this, and it's actually between a 2 and 6, depending also on the content. The final part of this work for now is JTPS, which is this JND aware 2-pass per title encoding scheme for live streaming that takes as an input various parameters like the resolution, the maximum minimum bit rates, the maximum VMAF, the target JND, and of course the input video segment. So you basically do that per segment, where you first extract these video complexity features, then you determine this perceptual optimized bitrate ladder prediction, and then the optimized CRF prediction for the actual encoding based on the bitrate ladder here, including information which encoder and preset you want to use to do then the encoding of the different versions in the second pass, and all can be done in live and basically in real time for each video segment. And the results also show here are also some figures which are compared to our previous versions like OPTE, PPTE, and also the brute force method as the baseline, so to say, where we could have, okay, we are not coming close to the brute force method, obviously, but still getting close to it, reduce storage size, but much better in terms of the percentage of the time compared, for example, to brute force or other existing methods here. Of course, the HLS standard bitrate ladder is much faster here. Shows a better improvement here. Anyway, Some of these applications, and I also need to look a bit on the time, is listed here. And if you're interested, just go on the website. You will find lots of examples and use cases where we have used VCA and tried to improve the bitrate ladder estimation. Let's now switch to content delivery, to the network part, where we worked on more or less network assistance for HTTP adaptive streaming. Here, mainly looking into edge computing support at CDN or the cellular network edge with different improvements with respect to prefetching, transcoding, repackaging, request aggregation, and using communications between host clients and the network itself, using SDN, network function virtualization, and so on. I picked up a couple of examples, and the publications you can see on the bottom. One is the space paper, is on segment prefetching and caching, where actually on the network edge, we have installed segment prefetching according to different policies. So based on the last segment quality plus. So you're not only selecting more or less the same quality as you did the last time, but also a quality representation higher and lower, or you just prefetch all of them, which is obviously the best one, but has storage constraints as well. And this prefetching could be also based on a Markov model, based on translating or machine learning tools where we use the random forest model, and also super resolution has been implemented on the edge as well, with kind of different results depending actually on the service provider's preferences and resources. So if you want to have low resource utilization, last segment quality and Markov based seems to be the best. If you want to have a priority on QE at the expense of costs, of course, there are other methods used. We also try to come up with a good balance, and here seems the machine learning based approach to be the best one, with again different performance results here on these different segment prefetching tools here, resulting into certain improvements in terms of QE, prefetching heats, caching heats, and the extra bandwidth needed for some of these techniques. And the previous approach space was mainly evaluated in a small setup. We also tried to run evaluations. ES-HAS is one of them, with a lot of clients in a virtualized environment, where we had like hundreds of different clients. Here in this case, we had about 60 clients to introduce new so-called server and segment selection approaches at the edge of the network to improve the user's QE and the network utilization. ES-HAS is one of that, where we introduced new components. One is a proxy that basically gets in the requests and then forwards it to the so-called network core layer or the caching servers or origin servers to fetch the segments and then distribute it and make it available to the client. So there are different components here. Using an SDN controller then helps here to improve the QE and the network utilization. That has been even further improved with the so-called work on Ararat, which is again based on edge tools, where you try to minimize the HAS client serving time and the network cost. And considering the available resources, there is a multi-layer architecture plus a centralized optimization model executed by the SDN controller. It has high complexity. That's why we implemented different heuristic approaches, coarse-grained and fine-grained. For fine-grained, we had 2 of them, and experimentation on a large-scale cloud-based testbed with 250 HAS players, where we could improve QE by like 47%, decrease the streaming costs by at least 47% as well, and enhance also network utilization. Again, you see everything close to 50% improvements compared to the state of the art at that point in time. A last aspect I want to present here in the network is on lightweight transcoding at the edge, LWTE. And here the idea is that we want to extract some features as metadata during the encoding process and reuse this metadata in the transcoding process at the edge. So you have like an origin server, you have the edge server. At the origin server, you actually encode the content in the different representations. you actually store only one representation, and for the other representations, you basically just store the encoding metadata that then can be reused at the edge server. So you basically extract the metadata here, you send it along the network to the edge servers, where you get one representation plus the metadata on how to quickly and fast transcode based on these metadata for the other representations as they are needed by the clients. So you have like the download and transcode mechanisms to be done here, and finally delivery towards the HAS players. There are some other variations. I have not the time to present that in detail. So CD is for cost and delay aware. So it focuses on the cost and the delay. And then also one approach is related to live. The first one that we have developed and is available here in this IEEE Access publication is on video on demand. For that, a binary linear programming model has been defined based on the various inputs like the video segment size, the metadata size, the resource costs, available resources that we have, probability function, number of the encoding requests. We generate more or less the segment service policy, whether a segment is stored, transcoded, or fetched from the origin, using the objective function to minimize the cost. That could be related to the computation, the storage, and the bandwidth, and the serving delay, which then provides also good results here. Oh, I still have it here, but I suggest to skip it here. There is an overview here. I can share the slides later on, and then you can probably read that in more detail. But now for the time being, looking a bit there, let's go to content consumption, the player part, and end-to-end aspects. And here we did a long list of different aspects here, starting from the player adaptation logic. And of course, the focus is on quality of experience. Let's just jump right now into some examples. But first of all, an overview of the bitrate adaptation schemes. There are tons out there. And in 2019, we have did surveys and tutorials paper published where we clustered these bitrate adaptation schemes into client-based, server-based, network-assisted, and hybrid adaptation schemes. Client-based, mostly it can be divided into bandwidth-based, so the adaptation algorithm that the client just takes into account the available bandwidth. Buffer-based doesn't care about the bandwidth, but just looks at the playback buffer, and if the buffer goes down, it does something. If the buffer level increases, it also does something. Then there are some approaches that use both of them. Of course, there are many proprietary solutions out there that the vendors produce, and MDB-based solutions. In the hybrid adaptation schemes, SDN-based or server and network-assisted schemes seems to be also quite popular and probably are rising in the future again. Our contribution to that is WISH, which is a policy-driven ABR algorithm that basically is based on a weighted sum model for HTTP adaptive streaming. That's also how WISH, the acronym, is created, taking into account the data cost with a weight alpha here that is related to the segment bitrate and the throughput, the buffer cost, which is related to download time, buffer occupancy, and the quality cost, which is video quality, distortion, instability. These metrics go into that cost, and everything can be combined towards a total cost. I just have a very quick overview on the results here compared to existing ABRs. You could see a bit of an improvement, but that's not really the point here in terms of the QE. It's just that you can configure it according to your needs. If you want to focus on quality or on the data cost, it allows you to create configurable ABR algorithm for different customer needs. This has been published in the MMSP workshop. And also a nice thing, it has been now implemented in the bit-moving adaptive bitrate streaming player. So it can be also used now there in a proprietary format, which is a nice success for our project. But we didn't stop there. We looked and extended this to what we now call eWISH, which is an energy-aware ABR algorithm for energy cost, which is related to, again, bitrate resolution and frames per second. And that's just a very recent extension that has been presented this year. And some results are also shown here in terms of the QE and the energy consumption. So we could increase the energy consumption for the different tests, the QE for the different test sequences based on the way on how we determined the parameters here, and at the same time also reduce the energy cost because of this additional cost function here compared to how it was previously or with related work ABR algorithms that we have determined. Another work item here is a so-called CATWISE, and here a specific version which is on live low latency, and CATWISE stands for Cloud-Based Adaptive Video Streaming Evaluation. It's an open source tool, you can use it, CATWISE by the way as well, and which allows you to set up a scenario like here. You have a live source, you do encoding, packaging, encryption is not supported, but that could be added as well. You basically post this to an HTTP origin. You might have a CDN in between or not, and then you have the client for decoding and also then rendering itself. So it's a tool that can more or less create different EC2 instances, initialize server and client, and execute experiments in that way. The clients, they also run on EC2 instances. You have a server that generates a live stream and then allows, based on the configuration, to have different network profiles. And in the end, everything is stored in the database for evaluations. And you can create then such graphs as shown here in terms of the latency, in terms, here is the different latency using different ABR algorithms. Like we have used DashJS, HLSJS, and then other 3 different ABR algorithms. In DashJS, you can have the default algorithm, and then you have 2 low latency algorithms. You can set the target latency, and then you get different results here based on different networking profiles. But the results are not so important here. It's more like the test bed that could be used in this context here. Finally, again, coming back to live, but now from an end-to-end perspective, I'd like to present you the work done in Artemis. Again, you see we have the similar setup: live camera, origin server for encoding and packaging, CDN servers for distributions, and player. Usually there is a static bitrate ladder, or the sysadmin sets a bitrate ladder in terms of bitrates and resolutions. It could be fixed. It could be also content aware, like Netflix, but title encoding and other usages. But for live, that previously still it's in practice. It's not done in a dynamic way. The manifest is created more or less, made available to the client, offers him different bitrates and the resolutions, and then the client more or less selects whatever it is required. In Artemis, which is the adaptive bitrate ladder optimization for live video streaming, we came up with the idea to offer client a mega manifest, which means rather than just having small amount of different bitrate resolutions, configurations, we provide them a very big range of files, of representations, and let the player select what's best in their certain use cases. So they select representations with the bitrates that closely match what they like to have in terms of their so-called desire bitrates. And then we create a OTL and optimized temporary ladder for individual clients, encode the videos based on the subset, getting information from the live camera source, and then you get a subset of the representations being streamed to individual clients. We tested this and compared it with different static bitrate ladders in terms of QE, latency, and star in the Artemis approach according to different network profiles, which are shown here. And for the QE improvement, we got an average QE up to 11%. In terms of the latency, was down 18%, and also we could reduce the star improvement and reduce the stars down to 36% compared to when using these 5 static bitrate ladders taking from different company websites or other papers, which are shown here, just to have a comparison or a rich comparison here. At the end, I want to move a bit towards also quality of experience and want to also provide you an architecture on how to improve the QE for future services. Quality of experience, the term actually dates back to long time ago, but there was this Qualinet, European Network on Quality of Experience in Multimedia Systems and Services, and they defined within a white paper QE as the degree of delight or annoyance of the user of an application and services, which then results from the fulfillment of his or her expectations with respect to utility and or enjoyment of the application or service in the light of the user's personality and current state. You can find this white paper here if you want. Later on, we extended this also to immersive media services, which are shown here with the screenshot, and then integrated this into 6TOF HTTP adaptive streaming through point cloud compression, and also had objective and subjective evaluations on that, resulting then in the end into this tutorial paper where we came up with this architecture from the server where on the capturing and the scene merging and encoding at the server side towards the streaming, towards the final user, like a VR end user or the client itself, through different networks, where we have different virtual network functions, allowing for compression, encoding, transport caching, viewport prediction, decoding, and of course, rendering and QE monitoring, everything with a feedback loop through a intelligence or software-defined network, which allows then feedback loop for parameter adjustments to improve the QE. And this we have worked on for 3 degrees of freedom: omnidirectional video, volumetric video, and 6TOF imaginary video, which is related also to holography content that is currently here a hot topic in the imaging domain, not so much in video yet. Good. I'm looking at my time and I have 1 slide of content left. I want to talk a bit about the future of video streaming. And here I want to start with video coding, where I think from my point of view, we see different tracks. One is called like learned video coding or end-to-end deep video coding. There is this paper, an end-to-end learning framework for video compression, where they basically try to replace every module within a traditional video encoder, as shown here, with a so-called deep learning-based or neural network-based network that is doing the encoding, but on an end-to-end aspect. In contrast to that, there is the so-called deep learning-based video coding, where they identify, again, different modules from the traditional encoding scheme and try to replace, but only certain modules here with so-called deep learning-based modules. That's why you have like here deep intra prediction, for example, or deep cross-channel prediction, and so on, or deep transform encoding, and these kind of things. And the last one is where you have a neural implicit representation of videos, NERV, that came up in 2021. And I think in the last couple of years, significant improvements have been achieved here, which goes a complete different way. So rather than presenting a video in the pixel domain, which is called explicit representation for video, it uses a neural network to represent the video, which is then used at the client based on these network layers to generate the video on the network itself. I think these are very challenging tracks and ways to explore. All of them, they have some, I think, some meaning in terms of the standardization, because all of them are finding their way in standards. For example, I'm active in AMPEC, and all of that is being followed up and explored there with different results. And this is probably a separate talk where I can spend hours on talking about that. I just want to use the remaining last minute to talk about the video streaming itself, what can be done here. We have came up with a paper which is called Deep Stream, which is video streaming enhancements using compressed deep neural networks, where the idea is that you have not only the video itself that you stream towards the client, but also a neural network that helps to improve the quality at the client side in terms of, for example, super resolution or artifact removal, denoising, and so on. And the nice thing is that these deep neural networks you can also compress, associate to the video stream. There are also MPEG standards which allow to do this all in an interoperable way that allows then enables more or less different types of users. We just call them CPU and GPU users that correspond to devices that have only CPU capabilities or have devices where you also have GPU capabilities to execute these neural networks in an efficient model and then help to improve the quality. At some point in time, hopefully also in real time, which is currently still a bit problem here and there, but I'm expecting this will come up in the future as well. And last but not least, of course, generative AI for video streaming. Everyone talks about generative AI, not only in terms of the large language models, but also in the image and the video domain. But how to use it for video streaming? Not so many people have worked on it. And that might be also something we can discuss and explore in the future. I'd like to quickly acknowledge the Athena team, international collaborators, of course, including also Wasim here. Thank you very much again for inviting. Thank you for attention. And if you have any questions, I'm happy to answer them now.
Yeah, thank you very much, Christian, for your very interesting talk and very rich in terms of information for video streaming and coding. We have time for a question answering session. Of course, I have some questions, but I first give the floor to the attendees to ask their questions. So if you have any question, you can write it, I think, on the chat, and I will ask them to Christian. Maybe I can start by some questions at the time we receive questions from attendees. I have a question about what is the end-to-end latency we can reach today with using this different streaming protocol, especially protocols that based on Dash HTTP streaming. We don't hear you, I think. Mute me.
Yes, I'm sorry, I was muted. Yes, yeah. So it's a bit tricky. Yes, I mean Dash has been not defined for low latency.
Yeah.
This is something you need to, if you really want to have low latency like we have now in Zoom here, you need other protocols. But in the low latency, I mean, you can set here the target latency like to 3 seconds. I think it can be also achieved. I have seen some setups where they claim to have latency lower than 1 second, but the question is always on how is that scalable for massive amount of users. Like when you have now in Europe, we have now the European Football Championship. I'm not sure you follow that, and if there are people watch a stream, then that might have some still a big challenges. So but it already got much better. A couple of years ago, I still believe it was like around a minute, maybe even more, that you have the delay compared to the traditional broadcast, for example, that you receive over satellite or over cable or over terrestrial. Probably now we're down to like 20 seconds, maybe. In the real deployments. I haven't tested it that much, and I haven't checked it myself. Probably I should do that with the next game just to see to get a feeling. But in extreme cases, you can probably get down also to below 10 or below 5 seconds.
What do you think about quick protocol, for example? It is really a protocol that target, for example, latencies between WebRTC and Dash?
Yes.
And are you looking at this at MPEG, for example?
No, that's done in IETF. In IETF, as you probably know, there is the media over quick. and then also some MPEG people are there, and
Okay.
the idea here is again using the formats that we have in Dash already, and then reuse the stuff there. But in Media Over Quick, they are looking into that, but I'm not sure how far they are yet. And I just know one guy really working in the research area on that. It's Ali Began. You probably know him as well.
Yeah.
He has created also, I think, some test beds where people can play around.
Yeah, I
And
think
that's
we will have a talk in September about around these topics to see
yes.
the ecosystem. We have a question
Yes,
from
on the low latency, I think it's the best to ask him
yeah.
because he spent more time
We
on
have
that.
a question from Carlos Fauzi Badr. How you see the role of Gen AI? This is related to your last slides. Can
Yes.
play on the video streaming reduction of latency. What is your opinion on the main bottleneck limitation to overcome using Gen AI for video streaming and latency reduction specifically?
On the latency, I'm not sure. Yeah, I at the moment I never was a really big believer on this latency issue, yeah, because uh, for me the use case was always a bit. Uh, I I didn't believe in that much. So for me, like in a live stream, if I have like 10 seconds delay or 20 seconds delay, probably it doesn't matter a lot.
And
I
what
know,
about
yeah.
in general for video streaming and
For generative AI, I think there are many possibilities
Mhm.
that you can use. There are a lot of things on always depending on the capabilities of the model that you have to generate content on the client. Overall, I think the target should be to stream yes as to stream less data over the network. So to take the content away from the network or maybe also from the storage and let the devices generate the content based on Gen AI models. But actually how you do it and what you can do it, there is a rich feature space here, that research space that could be done here. Yeah, I mean, it could
Yeah,
even start with just some super resolution, which you also say it's some kind of Gen AI. In fact, it's not, as we know. I mean, in the end, maybe you will just send text prompts to the clients, and the client will generate the videos.
yeah, I think wireless communication community started looking at this in terms of they call it semantic communication, how you can send like prompt to
Okay.
uh, this diffusion model to be able to generate something according to
Yeah.
the goal we are optimizing.
I think the main issue there is that the current models they are not producing deterministic results. So if you send the
Yeah,
prompt first time and then the second time the same prompt, you will get two different results.
yeah. We have other also interesting questions, I think, related to your first comment. Thanks for the presentation. My question is about live video streaming. Why is the focus on HTTP if we are not able to reach 1 second end-to-end latency, less than 1 second
Okay.
end-to-end latency?
Okay. I think it's the scalability. In
Mm.
deployment it's all about scalability. And with a Zoom call, for example, where in real-time communication protocols are used, as you probably know. I mean, it's you need lots of resources to set it up to let millions of users. Just imagine, I think one of the biggest live streaming events nowadays is probably the Super Bowl, American football event, and that couldn't be done, I think, probably with technologies like we use that in Zoom calls right now. So scalability is a big concern, and that's why still HTTP adaptive streaming is used. Maybe this media over quick, will solve the problem, and we'll try to because the goal is really to converge the classical video streaming domain with HTTP dash and HLS, and then the video communication community with WebRTC into like one architecture using the QUIC protocol. And there, if you have looked into that, they have defined a publish subscribe mechanism where probably this can be solved in terms of the latency and also in terms of the scalability. But yes, we will see if we
Yeah,
will,
this is very,
this
I think,
goal will be
interesting.
reached. And of course, there is still also a possibility to do some research. It's mainly dominated by companies. I think now they are working in that, and lots of startups and academic institutions are not so much involved, except I know one, and I already mentioned the name.
And another question maybe from Ahmed is, what is how do you think about using generative AI for adaptive streaming, like in terms of adaptation?
That's something we are looking into currently right now. It was a bit here in the deep stream architecture. It's considered that you could have, for example, for every representation, you have your own neural network that helps then to improve the quality. You could also think about scalable neural networks, like scalable video streaming. You have scalable neural networks that when you add more information, it does a better job at the client side. I came up once with the idea, I had no time to follow it, to think about whether it also makes sense to have a adaptive streaming of the neural networks. But this is just an idea I had as a question. Does this even make sense? Should we do something in that domain? Do we need then also some standard support, maybe from Dash point of view? But I was never able to really work on that, and also didn't
Maybe
find.
one last question is about energy consumption of video streaming. What do you think about these research topics? What are the latest trends for this, how we can
Yes.
reduce energy consumption? And is this topic addressed at MPEG, for example, in terms of signaling in the dash, in the MPD?
Yes. I think it's a hot topic. We do some research. I have not covered it here in my presentation. We have a different project. It's called Gaia, where we actually work on that to also have this live per title encoding and then trying to improve energy consumption. We started measuring it, and it could be also taken into account in terms of the encoding, just to improve also resource usage in the cloud, because in Bitmovin, for example, everything is encoded in the cloud and you can better utilize cloud instances for doing the encoding job. It's also related to the scheduling of the tasks within the cloud. And finally, at the client, there are also different ways on how to, for example, reduce illumination in an adaptive way. Background illumination. Brightness of the content is, I know some people are studying, or just having like on the player a kind of echo mode that could be as simple, just excluding 4K resolutions because they consume more energy than full HD. So there is lots of research in MPEG. There is green MPEG, I think. Where they include SEI messages, which could be then signaled with the encoded video bit stream, and then utilized at the client to operate in a energy efficient mode. But I don't know the exact details. If you need Dash support here, there is some discussion ongoing, but not so much. I don't think that there is any good draft available. Also, just because they just put it as SAI messages, which goes into the video stream, you don't need to put it into the MPD anymore, because just the client decoder can utilize this information. If the client understands these SAI messages, then can put the client into a reduced energy, or how we called it, echo mode kind of thing, to consume less energy.
And maybe one final question we have just received from Brahim Farhad. I think it is related to the current activities on the next generation video coding standard, H267. Do you think there is still room for evolving the classical approaches for video coding without using AI? Like this is, I think, how we can develop the next standard with controllable complexity?
Yes, yes. Well, complexity is a different thing. Let's
Yeah.
keep that out for the moment. But I think in terms of the input contributions, there are more input contributions like using traditional video coding and improving it there. That's a bit funny. Yeah. You need to follow my Twitter account. So when I'm attending the MPEG meetings, I usually then tweet out the latest results. Every meeting, they make comparisons. I can send you was in the link of the latest comparisons from the last meeting. And there are some nice slides, or I can just send you the slides of the presentation. They show some comparisons of traditional improvements without AI. And they have this other track which they called, I think, neural network-based compression to show that. But in the neural network-based compression, runtime complexity is much, much higher compared to the traditional approaches. But they're still working on that, and they are still, getting good results. I just have the fear that the neural network-based video coding people have a steeper, so say, learning curve or a performance curve in terms of catching up with the traditional codecs, and sometimes might go in front and might produce better results.
I saw the report from the last meeting, MPEG meeting. I think they are reaching around 50% of bitrate reduction compared to VVC, with almost 10 times encoder complexity and also 10 times decoder complexity, which is quite interesting. Let's see if they will maybe launch new standard activities or not.
Yes, I haven't followed up CVPR, which was, I think, last week or 2 weeks ago, if there are some new results in terms of the nerve, but we are currently analyzing this and trying to find out if there is a new version.
I think we are at the end of this talk. So I think you answered all of our questions. I think I would like to thank you again for your time and accepting to give a talk and participate to this TII seminars series. It was very interesting to get all this information, insightful information about video streaming. So thank you very much, and we wish we can meet in other events, conferences, or MPEG meetings in the future.
Thank you for inviting me, and if you have any questions or comments, just let me know. Drop me a note. I'm happy to
Thank you very
respond.
much, Christian, and thanks to all attendees for attending this talk.
Thank you. Bye-bye.
Thank you. Bye-bye. Have a good day.